Today's lesson has nothing to do with systems of equations, but matrices, which this is a matrix here, matrices allow us a couple of other ways to solve a system of equations. So that's why matrices are part of this chapter 3. But before we can actually use matrices to solve a system, you just have to know what a matrix is, how to work with matrices in general. So today we're looking at how to analyze data in matrices, so how to set up a matrix, because these can be used as ways to organize data as well. So how to analyze the data in matrices, and then also we'll look at how do we add, subtract matrices and multiply them by what's called a scalar, which is basically just a coefficient for a matrix. So that's what we're looking at today. Monday and Tuesday next week will be a couple days of multiplying matrices, because multiplying matrices is much more complicated than just adding and subtracting them. We don't do anything with division for matrices. And then after we multiply matrices, we can start looking at the two different methods that we can use to solve a system using matrices. So how many of you have, when you see this, have any of you worked with matrices or learned about matrices before? Okay. So a matrix, it's a rectangular array of variables or constants in rows and columns. Usually it's enclosed in brackets. In a matrix, the numbers or data are organized so that each position in the matrix has a purpose. Each value in the matrix is called an element. So if you see that terminology, like the element in row 1, column 1, element is just whatever is there, whether it's a number, variable, expression. And it is usually named using an uppercase letter. So you can see this matrix, they're calling matrix capital A, and it has these 12 values in it. So matrices have rows and columns. And so you can see now this, it might seem self-explanatory to you, but as we get into it and you have to deal with the dimensions of a matrix, it's easy to get rows and columns switched around in your mind. So rows are horizontal, columns are vertical. So this matrix has 3 rows. So rows horizontal. And then it has 1, 2, 3, 4 columns. These are vertical. And then this is just referencing, we are not going to name elements by using this notation, where they say the element -1 here in row 2, column 1 can be depicted by this lowercase a, since the matrix is capital A, and they call it A sub 2, 1 for row 2, column 1. We don't have to name the elements that way. So that information is on there in case you see that, but that's not something I'm having you do. But being able to reference a number, like which row, which column it's in, is important. So if I say row 2, column 1, just to know that, okay, I'm in row 2 here, and then column 1, I'm talking about this number here. The rows and columns are also very important in describing the dimensions of a matrix. The dimensions will tell you whether or not two matrices can be added and subtracted, as well as multiplied. So the dimensions matter for what operations you're able to do between two matrices. And for the dimensions, it says here, a matrix that has m rows and n columns is an m. We read this as m by n. So that's in parentheses after it, m by n. But it's written as like m times n in a way. So it's rows by columns. So the matrix above that has 3 rows and 4 columns is a 3 by 4 matrix. And that's where it's easy to get those switched around. So if you say the matrix is 4 by 3, that's something different. It doesn't maybe seem totally different, but it is very different. So we'll be looking at dimensions today and the next few days as we go through the operations that we're able to do. And then we're going to be going through an example where we're setting up a matrix and then analyzing, interpreting, determining if some of the data questions that are asked even make sense to answer. So if we look at example 1, it says Caitlin wants to attend one of 3 Iowa universities next year. She has gathered information about tuition, which they're calling capital T, room and board, R/B, and then enrollment E for each of the universities. And we have Iowa State, University of Iowa, and University of Northern Iowa. So part A is organize the data as a matrix with the, and it tells us this, columns in the order of tuition, room and board, and enrollment. So how I'm going to set this up is my column. So vertically, I want my first column, I'm just going to put a T. I want all of the tuitions. My second column, I want all of the room and boards. And then my third column, I want all of the enrollments. And therefore, so those are my 3 columns. So what are my 3 rows going to represent, or what are my rows going to represent? How could I label the rows, Jocelyn? The schools, yeah. So I'm going to abbreviate Iowa State. I'll just abbreviate this, like call this ISU, call this just UI, and then UNI. Just so I have a label here. Okay, and then I'm going to fill this in so you can see we're going to have 3 columns and 3 rows, and I'll fill in those values. So for Iowa State, for my first row, if tuition is first, 6,160, room and board next is 5,958, and then enrollment, 26,160. And I'll do that for the other 2. And then not including my labels here of the rows and columns, but I will put the brackets around the actual values, since that is typically how you're going to have a matrix written with the brackets around it. So these dimensions, the dimensions of this matrix, rows by columns, I have 3 rows and I have 3 columns. So this would be a, not that it asks for this, bless you, this would be a 3 by 3 matrix. I just want to try to get you familiar today with looking at the dimensions, since we need it as we move forward. Okay, and then we're going to be asked some questions about the matrix and whether or not things make sense as well. So question B, it says find the average of the elements, so the values in column 1, and interpret the result. So if I go to column 1 and I find the average of those 3 elements, how do I find an average? Yep, add them all together, divide by how many there are, which I have 3. So I'm going to write it out. You may not need to for your own notes, but that's up to you. Anybody have what the average is already? You've calculated it or no? What was it? Thank you. Okay, and then it says to interpret the result. So what does this 5,935 represent? Isaac? Average tuition. So this would be a dollar amount, since all of these tuitions are dollar amounts. And 5,935 is the average tuition. I'll put among the 3 universities. Okay, so in terms of interpreting and analyzing, this is a value that they would call meaningful, or it would make sense to find the average of the three values in column 1. You get a value that means something. It means the average tuition for the 3 schools. In part C, it asks, would adding the elements of the rows provide meaningful data? And again, meaningful is not like would it mean something to you personally, but just the value you get. You have to think about what that value represents. Does it make sense, basically, to add those elements together? So if you go across a row, would the number you get be a meaningful number? Yes or no, and then why? Or would it make sense to add the 3 numbers that are in a row? I see some no's, Alexis.
No, even though the first 2 deal across the third one to enrollment, but that's not possible. Also, it would make sense to tell how much money you have to put into school.
Correct, yes. So these 2 values are dollar amounts. This is a number of people. You wouldn't add a total cost or a tuition and room and board cost with people. So would adding the elements of the rows provide meaningful data? No, because I'll say the first 2 columns represent costs, and the third represents a number of people. So it's basically just making sense of the numbers you have there. Since you're not putting the units also in the matrix, it's just making sure that you remember, because the matrix, again, is just a way to organize data. It's kind of like a spreadsheet. It's just an organizational tool. But just making sure you remember what the numbers actually mean and whether or not mathematical operations within the matrix make sense. Part D is a similar question about whether or not something is meaningful. So it says, would adding the elements of the third column provide meaningful data? And then explain. So again, meaningful just meaning would it make sense to add them? The yes or no is kind of like what would you get? What unit would you put on it if you did add them together? So in that third column are those 3 values you could add together? And if so, what would you get if you added them together? First of all, would it make sense? Would you get a number that makes sense? Okay. And then the number that you'd get, what would it represent? Not the average, because it just says adding them together. Yeah, the total. So yes, if we added the 3 values in the last column, that would be the total enrollment for all 3 schools. So say yes, this would be the total enrollment of all 3 schools. Okay, any questions? Setting up a matrix. This is just something that I think we kind of get in the habit of maybe overlooking. Is it's always important to make sure any answer you get in math makes sense or is meaningful, and then what it actually represents. So that's really what this is having you look at. All right. The next part then is looking at how to add and subtract matrices. So algebraic operations, addition, subtraction, and then I said multiplying by a scalar, which is like a coefficient for a matrix. So it does say here, when it comes to dimensions of matrices, you can only add or subtract matrices if they have the same dimensions. So they have to be the exact same size matrix in order to add or subtract them. So it is not possible to add all matrices or subtract all matrices. And so this just lays it out for you. But basically in words, to add or subtract two matrices that have the same dimensions, you add or subtract their corresponding elements. So this is just showing if I have matrix A plus matrix B, I can add the corresponding element. So the element that's in row 1, column 1 with the element that's in row 1, column 1. The two elements then the same position, added together, go in that same position in the answer. Same for subtraction, and then it gives an example that actually has values in it. So if we were to look at example 2, there's 3 under here. It says find each of the following 4, and it gives 3 matrices A, B, and C. And A wants us to add A plus B. So I'm first, I know they're right there, and again, you working through this on your own might not need to do this. I'm just going to rewrite the matrices here. So matrix A, I'll write down plus matrix B. And this is, again, if you remember from the ACT pretest, you had a question that was just given like this. I think it was subtraction, but it was given set up like this. So first of all, visually you can see that these two matrices are the same size. And what would the dimensions be? 2 by 2. The square matrices, the ones that have the same number of rows and columns, obviously are the easiest because even if you had rows and columns switched around, you'd still have the dimensions correct, but 2 by 2. So then I would just add the corresponding elements. So in my answer, I'm adding the 16 plus -4, and that goes again in the same position in your answer matrix, so that's 12. Then in row 1, but column 2, the second one, 2 plus -1 is 1. Now into row 2, -9 and -3 is -12, and 8 and -7 is 1. So this matrix is my answer. So when you add or subtract two matrices, again, they have to be the same size. Your answer then also should be that same size. All right. Part B says to subtract B minus C. So again, I'm just going to write that here. I know they're given at the top and you may not need to. And then C looks like this. So visually looking at these, you can see they're not the same size. So this is not possible to subtract these. So you would just give the answer not possible. You don't need to put no solution. Again, when you say no solution, it should be only if you're asked to solve an equation, and then you get no solution for that equation. So this is just an expression, subtract the matrices. It's not possible to do that. So we already talked about how B was a 2 by 2 matrix. This then, what would the dimensions of this matrix C be? Not 1 by 1. Close. It's 2 by 1. So remember, it's rows by columns, and this is where it gets tricky because you have to think like the 8 is a row, the 6 is a row. So there are 2 rows, and then there's 1 column. So that is a 2 by 1 matrix. All right, and then we have B minus A. And we already know A and B are the same size. Here, though, you just have to be careful with subtraction, that you carry the subtraction sign through for all of them and you don't start to just add the elements together. So I know these are both 2 by 2, so I can subtract them. Like I said, you just have to remember that you're subtracting. So as I'm doing this, I have -4 minus 16, so -20. And then -1 minus 2 is -3. Here's where you need to remember it most when you're subtracting a negative. So -3 minus -9 is really -3 plus 9. So that would be 6. And then -7 minus 8 is -15. So just in general, we'll always have to be more careful with subtraction versus addition. But any questions, adding, subtracting matrices? The biggest thing is they have to be the same size. More so on Monday and Tuesday when we're multiplying, because visually you can tell if two matrices are the same size. So I will just kind of clue you into this as thinking ahead. Even though these two matrices cannot be subtracted, I could multiply these together. However, if I would have written these dimensions down as 1 by 2, like if I thought this was a 1 by 2, my conclusion would be, oh, I can't multiply them. So that's why actually knowing and being able to name the dimensions correctly, that's going to tie into whether or not you believe you can multiply them. And so that's where that is important. These two could be multiplied, but if you had switched this around and said 1 by 2, you would conclude that you couldn't multiply them, and then that would be incorrect. So we'll talk more about that Monday, but just kind of foreshadowing there. Last thing, we have, like I said, multiplying by a scalar. This is called scalar multiplication, and it's basically when you have, like I said, a coefficient in front of a matrix, what you do is you multiply each element in the matrix by that number. So it's almost like you're just distributing that number in, but everything in the matrix gets multiplied by that value. So that's just showing here if I have some number k multiplied by my matrix, I multiply every element in the matrix by k. Not too bad. So if we look at example 3, this is how it might be written. It says if R is equal to, so here's matrix R, and then it says find 5R. So 5R is just multiplying all of my values by 5. That's all it's asking you to do. So you're still going to end up with the same dimensions you started with. So -12 times 5, this would be -60. I'll go across the rows. 8 times 5 is 40. 6 times 5 is 30. And then row 2, -16 times 5 is -80. 5 times 4 is 20, and 5 times 19 is 95. That's all you need to do there. It doesn't ask us this, but what would the dimensions of this matrix be? 2 by 3. Two rows, 3 columns. I'm going to have you look at example 4. So this is now putting those operations together. It's basically an expression, but with matrices, and you need to follow order of operations. Order of operations is the same with matrices as it is for just numbers. So it gives you two matrices, matrix A and matrix B, and this is the expression that you are trying to find. So it includes the scalar multiplication and it includes addition. Okay, so find -6 times B plus 7 times A. What would your final matrix be? And then once you have that, I know the assignment, it is out of the book. However, if you look at the back page, I have the problems that you need from the book copied there. So you might need, you would probably need like a separate sheet of paper to do the problems on. I don't have a separate worksheet to give you, but all the problems are on the back here for that practice. But look at example 4 first.